So today I want to tell you guys a bit about some of the work that we do at Quantum and Complexity Sciences Initiative. So this is a group that I lead at NTU. So what we focus on is a lot of the interface between complexity, thermodynamics, and quantum computing. And naturally, one of the key areas that we are interested in is the fundamental energetic costs of computers, depending on whether we process classical and quantum information. And in this context, especially in line with our last talk just before lunch, it'd be good to, one of the key ideas that we are thinking about is the role of machine learning and how that interfaces with energetics and computation. And naturally, we heard already how deep learning can help us in optimizing quantum gates. And, and indeed, deep learning can help. And we are using automation to not just mitigate non-Markovian noise in quantum computers, but also to sort of understand things. Am I using this one now? Okay. Also, to understand sort of autonomous vehicles, automated trading. Basically, we are seeking this automation of ever more complex tasks. And one area in which we can think about these things as physical objects is to think about them as autonomous machines, autonomous agents. And roughly speaking, autonomous agent is just some object that receives inputs at certain time steps and makes decisions about what actions to take. Usually with some sort of goal in mind, in some way that they want to influence the future, such as my daughter here, who consistently wants more ice cream. Now, of course, they are much more physical operating relevant things, but as an illustration of, say, this ice cream choice, it's to get the best strategies, we require contextual thinking, adaptive thinking. The idea is that the agent makes decisions online based on what they have seen before. As a toddler, the maximization function, or the objective function, is to get as much ice cream as possible. And therefore, you see that the answers to subsequent questions depend on what was asked before. In many psychological tests, they've shown that if you ask the toddler, do you like ice cream or do you like broccoli, before asking them, are you hungry, the answer to are you hungry is going to depend on which question was asked before. So even at the level of a 2 to 3-year-old, we humans have got a good grasp at adaptive or contextual behavior. And to do so, of course, the classical explanation, not claiming quantum psychology here or anything, is that these toddlers have memory. They need to remember things about what has occurred in the past. So to be able to answer these questions adaptively, what our agent has to do is it has to sort of recognize some information about what questions are asked, record that in memory, because only then can the agent make different decisions despite having sort of the same input stimuli. If we cut off this memory, what we see is that the agent at each action is just another channel, and we just have memoryless channels whereby the same input elicits the same output response. But by having this memory, we can get these different output responses, even though we have the same input at the particular time step. And this is really the key thing that allows automation to perform highly complex and adaptive tasks. And as we perform tasks that are much more complicated than simply trying to optimize for ice cream consumption, such as, say, large language network, sort of language processing, large language models, etc., we find that we need to track correlations in information far into the past. To understand the context of speech, for example, we really do need the entire conversation to extract the key features over a very long temporal timescape. And indeed, as we do that, what we find is that there is a vast memory energy explosion. If we look at the current scaling, especially with the new transformer models that attempt to record absolutely everything, what we see is that the scaling is currently at around about 275 times every 2 years. Now that is 2 orders of magnitude in excess of Cormy's law, which was introduced earlier in this conference, where we're roughly doubling in energy efficiency about once every 2.6 years. So with that in mind, something really has to give. And indeed, by current projections on energy supply, the amount of processing power using for AI is expected to exceed global world energy production somewhere around the 2040s. And obviously, that's not going to happen. We will be energy constrained long before then. But this gives you sort of a picture of how kind of unsustainable current growth is, which is why in the classical setting of machine learning, there's a keen interest in finding ways of doing model reduction, to be able to, after we train a model perhaps, find the best ways of reducing that model in a way that makes it more palatable when we apply inference or apply execution. And some of the common methodologies, for example, is to take the continuous parameters often in our neural networks and approximate the large 32-bit floats with something more discrete, say maybe 2 or 4-bit floats in the extreme cases, in a process that the classical computer scientists would call quantization. Not to be confused with true quantization. There's no quantum here whatsoever, but they probably use the more true meaningful quantization, which simply means to make things a bit more discrete. And of course, there are various different ways, like clustering, various ways of choosing these time steps, etc. But in essence, there's always a trade-off between memory, how much memory we use, and how much distortion or how effective our models are, from sort of just doing random coin tosses at this extreme to recording absolutely everything we could possibly do. And of course, that trade-off also elicits memory energetic costs. Now, I'm not claiming to be an engineer, so what I want to study here and talk about is really the ultimate limits. I want to understand, okay, given this explosion, and I think we just stopped. Hello? Oh no, that's okay. Now, so given the need to find more efficient models, what is the fundamental energy cost for executing these adaptive online strategies? So is there a fundamental cost? We see that maybe there isn't, because after all, we can make computers reversible, as Oeda mentioned. So is there a fundamental cost when we try to do this adaptive behavior? And can quantum agents supersede these classical bounds? Now, to tackle this question, a little bit of formality, just an illustration of how complex these strategies typically are. If we wanted to define them mathematically formally, we need to think about an entire family of stochastic processes parameterized by every single possible input that we could give them. So while we can specify a strategy exactly, it is an immense computational task. We generally do not do this. Typically, what we think about is to execute them, of course, in these finite state machines, where at each time step we have some input and we have some output, and that memory updates along. But we can think about, from a theoretical perspective, we are given a specific strategy that we want to achieve, the theoretical optimal for perhaps performing some game. Then the question in terms of memory is, how much information do we need to track about what has occurred in the past, so that for every possible future input, our machine or our agent is able to give the right statistical output behavior. And the question then is, okay, what is the memory, or what is the amount of information we need to communicate? And if we could track that amount of information, or have that amount of energy to track that information, then we have an agent that can execute a particular strategy faithfully. Now, for our formal framework, we're going to make a few formal assumptions. The first two deals with basically no pre-knowledge and input preservation. Our motivation there is that we don't want our machine to be harnessing the input stimuli as a source of free energy. So the input stimuli should be completely sort of unknown, the distribution, to the agent. The agent has to treat that in an adversarial perspective, and the inputs must be preserved so that we can't turn the ordered input states into disordered states for energy consumption. And of course, the second two deals with, assumption 3, deals with no free memory, in that we can't sort of just extract free bits of order from the environment as a source of free energy. And our final assumption being that our input and outputs are always classical, even if our agents are quantum mechanical. This allows our quantum agents to be compared in a fair way with their classical counterparts. Now, with that in mind, our full framework for our agents can be thought of in this form. Basically, we have the machine, the agent coming through here, and at every time step, it receives an input stimuli, which needs to be preserved so that its free energy is not harnessed. And at the same time, there might be some thermal tape that the agent is required to write its output action on. The policy at each time step is the same, because the only way the agent can respond to adaptively to behavior is to transmit that relevant information in memory. And what we end up is what many of you may be familiar with, known as a quantum comb for modeling non-Markovian systems. But if you're not never heard about that, no worries. All that the question we're asking is, to execute this comb-like device, what is the minimum energy cost if the policies were quantum versus if they were classical? Now, to understand that, we need to do a quick diversion to information thermodynamics. Now, Thankfully, due to OIDA, we've already seen a nice coverage of Maxwell's demon, so I'll be very brief here. The point I want to emphasize here is that the first agents came from physics, and the first agents were Maxwell's demons. If you think about where agents came from, we now think about mainly from the computer science perspective, but Maxwell's demon really encapsulated everything there is about the autonomous agent. It was a machine that observed the environment, and depending on what it observed, it committed that observation to memory, and based on that memory, decided how best to extract free energy from an environment that apparently didn't seem to have any free energy to begin with. And we saw from Aoida's talk that the resolution to this was that, that there was some memory that the agent needed to have, that the agent needed to record within it some information about the environment so that it could respond adaptively, and that once we account for the energetic cost of resetting this memory, then we we no longer violate the second law of thermodynamics. So the key resource here is that memory, and the key thing about both Maxwell's demons and autonomous agents is about the thermodynamics of this memory. Now, we can generalize the initial results about Maxwell's demon into a more general case of information thermodynamics, which again, thankfully for this morning's talk, I'll just skip through very briefly. In summary, basically when we have a computation, if it erases some information in the sense that the entropy out and the entropy in differs, and we can think about that as a free energy gain or the free energy loss, then whatever the case, the work required to perform this process exceeds that of the change in free energy. And this work process here is basically, this kind of guarantees that our second law of thermodynamics is preserved. Now, in the quantum perspective, everything can be quantized using the framework of information batteries, first introduced by Feist and Renner. The basic idea is if we have a generic quantum process, we can analyze its energetic cost formally by thinking about it as some unitary dilation, some unitary coupling to an external ancillary information battery. This information battery being just a pool of maximally charged batteries, so pure qubits and maximally mixed qubits. And then the basic idea is that once to enact this unitary process, we invariably have to change the state of the battery so that the state of the battery before and after the computation is different. Now, this could be because entanglement is generated and we're tracing out part of the system and so forth, any number of ways, but suffice to say that whatever the case, what we end up is if we perform this computation in the IID limit, so we perform this computation many, many times and got many of these batteries in the limit that n tends to very large, and then we look at the free energy loss of these batteries or the amount of energy needed to restore these batteries to their original state. The work cost is going to be in excess of the free energy gain of the quantum system itself. And in this way, we can map the microscopic ideas of the thermodynamics of quantum computation to the macroscopic IID limits of macroscopic quantum thermodynamics. And we're exactly going to leverage this information battery formalism to understand the energetic cost of our agents. Basically, we think about our agents as something that receives the input stimuli and then gives the output. But to do that, it needs to make a decision here. It needs to translate the input to the output in the cycle. And every time it does a cycle, it needs to expend energy. And then what we're going to look at is when we execute many of these agents over many time steps, what's the average amount of free energy we need to use to reset these batteries on a per battery basis. The key thing that I want to emphasize here, and a particularly nice element about this framework, is that the computation itself is unitary interaction. So it can be done in finite time. There's no need to go to the adiabatic limit to reach the limits of what we can do thermodynamically. To reach those limits, all we need to do is make sure that the batteries themselves are charged adiabatically. So you can imagine the agent operating in real time, and we're collecting all of these wasted batteries, which we bring to some petrol station, well, some information battery station to recharge. And so under this framework, we can then do a more careful analysis of the exact thermodynamics of these agents. In particular, the first thing we wanted to look at is offline lower bound. That's to say, if we we removed all the constraints of this agent having to respond online, and let the agent collect all the questions and then answer them all in one go. So the agent can respond to everything at once. Then what we find, of course, is we can think about it as just a single process that maps the input to sort of the inputs as well as the output actions. And when we look at the entropic differences between the output and input, we can see the ultimate free energy gain of this process. And when we compute that, we get something of this form. And since we can always saturate that, either by classical or quantum means, since all the outputs here are classical, there's not going to be a dissipation advantage here for classical and quantum agents. In fact, both of them can operate perfectly reversibly without any dissipation using sort of reversible computing. And so there's no quantum advantage at all if we're looking at these things offline. So really the key element here for having this difference is being able to respond in real time, being able to respond online. And that's where we do get those differences. Because if we start thinking about these agents so that they have to act time step by time step, so at every time step they have to decide on the next output before they see the next input, then what they'll be updating is this memory. And once we factor this memory into account, what we end up is an equation of this form. This investment of energy due to the need to correlate the memory with the input and output. And as Oida has mentioned, that correlation that's established on mutual information does cost free energy. And of course, these second two terms are basically still functions of only what we observe, the agent's input and output behavior, so they can't really be changed. They're the same as long as we require the agent to execute the same strategy. So the key thing is that the more the agent remembers about the immediate past, the more energy it needs to use. And so so by looking at this way, we can then compare the energetic costs of an agent operating online with the free energy gain or the energetic costs of an agent that can wait for all the responses. And when we take the difference of those and look at the energy rate, so the extra energy used per time step, what we find is a difference between two mutual informations. The first, roughly speaking, is the amount of information the agent needs to commit to remembering its current input stimuli. And the second is how much that information is actually relevant for generating the next output action. And it's a difference in these mutual informations that tells us the energy dissipation or the fundamental irreversibility per time step. And this is an irreversibility that cannot be removed through reversible computation without making sure that the memory of the agent scales as we store more and more time steps. So if we want the agent to keep the same policy and to respond the same way on a time step by time step basis, this energy dissipation cannot be avoided. And so once we have this, when the intuitive way of thinking about this is that this is kind of like the energetic waste on a time step basis. The agent is kind of recording a certain amount of information about the past stimuli, but only a subset of that is reflected when generating the next output action. So at every time step, some of this information is wasted, that is recorded, and when that's dissipated into the environment through the computation, that necessarily generates heat. Now, once we have that then, given two models, the model that necessarily sort of records less information about its immediate past is going to be the one that is more energetically efficient. So the next question we ask is, what are the fundamental limits? And can quantum agents reduce this heat dissipation now that we have this terminology formalized? And while the formal proofs of this is a bit too involved for this presentation, I can illustrate these things with a fairly simple example. So here is an example of a quantum replicant. So it's taken off Blade Runner. The idea is that we have a simple agent, and at every time step, he is posed one of two possible questions. Do you like electric sheep? And are you human? And the required observed behavior for this agent is that he has to satisfy two conditions. First, if he is asked the same question consecutively twice, his answer must be consistent and agree with his previous answer. Second is that if he was asked a different question, he is required to answer randomly. Now, if we look at the classical representation of this agent, the simplest finite state machine and the most thermally efficient machine needs to track two bits of information, both which question was last asked and what was the answer last given. From those, we can build this stochastic machine that is able to generate the expected behavior. And the basic idea is that each one of these 4 states corresponds to one of the combinations of which question and which answer, and from that, the agent can make a sensible decision. Now, we see then that this requires, roughly speaking, 2 bits of information, assuming that the agent has no knowledge of what question will be asked. Now, so once we have these 2 objects, let's see whether we can simplify things quantum mechanically. It turns out that quantum mechanically, in this case, the memory that the agent needs to commit is only a single qubit. By this sort of encoding on the Bloch sphere, a bit reminiscent of random access codes. The idea is to compress 2 bits of classical information into a single qubit. While we cannot retrieve these 2 bits of information perfectly, due to Halevo's theorem, it is still sufficient for us to replicate this exact behavior. The quantum circuit looks kind of like this. It's a bit involved, but roughly speaking, if we look at it very carefully, it's actually a fairly simple circuit. Depending on what input is coming in, we apply a Hadamard gate to the memory. So this measurement to imprint the outcome is really simply a measurement either in the X or the Z basis, depending on the input. And if we think about it that way, then we come to a conclusion that this is really just a fancy way, a thermodynamically efficient way of conducting the Stern-Gerlach experiment. Because as we know with the Stern-Gerlach experiment, if we have a single spin, asking it 2 questions, measuring it in the same basis twice, elicits consistent answers, but measuring it in the other complementary basis gives us a random answer. And by leveraging that, we're able to build one of these circuits. Now, I won't go through the next 3 slides in the interest of time, but the basic idea is that once we analyze the source of the thermodynamic waste, the idea is that the classical agents, by storing these 2 bits of information, these 4 configurations, is storing too much data. Some of that data is never propagating into the future, no matter how we interrogate that agent. And indeed, if we do the thermodynamic analysis using the equations we drilled before, then what happens is that our classical agent records 2 bits of information about the immediate past. Our quantum records 1 bit of information. The rest of this deals with the free energy gain of the output versus input, and they stay static. And so we end up with an energetic cost that is half if we go from the quantum compared to the classical regime. We can then compare the energy gain of the ideal agent, of the ideal reversible agent, if we didn't have to respond to anything online, so the offline agent, to look at the free energy gain of output versus input. Once we kind of subtract these from each other, what we see is that the energy dissipation for the quantum agent is 1.5 kBt per time step. For the classical one, it's 1.5 kBt, and the quantum is 0.5 kBt. So we get an order of factor of 3 advantage for this simple device here, simply by going from classical to quantum. And once we can incorporate those information batteries and thermodynamics in the picture, in this case it's particularly simple because we're simply feeding in one single information battery at every time step to record the output. And then the output itself contains half a bit of free energy, allowing us to, in principle, extract that in the future. So the irreversibility of this entire process turns out to be half a bit per time step. Now, the results that we have derived, the first is that this turns out to be very general. As long as it's a non-zero causal waste for classical agents, it's always possible to construct a quantum agent that does thermodynamically better. And it turns out that in general, almost every input-output behavior, as long as it has some stochasticity into it, we will end up with an inefficient classical agent. And so in terms of the results so far, what I want to communicate is that, first of all, there is a fundamental energy cost for responding online. This is quite interesting because if we didn't require this online execution, then everything in principle can be done reversibly. But because we want our AI to respond to things in real time, that's going to incur fundamental unavoidable dissipation beyond that of the standard Landau's bound. And more of all, the quantum agents in this path can supersede their classical agents. Obviously, neither of them can violate Landau's bound, but the quantum can sort of improve us in responding online. In the last 4 minutes, just a quick outlook of where we're going so far. The first thing that we're interested in is currently scaling, because it's already results that quantum agents, for certain complex behavior, the memory advantage can scale with the complexity of the behavior. So as we look at more and more complex things, such as those maybe that are tackled by the large language models, we're expecting a much higher difference between the classical versus quantum energy dissipation. In principle, of course, all the engineering overheads notwithstanding. The second thing is that this could be used as a way of benchmarking, especially if it scales. If we could look at the fundamental dissipation costs for executing certain complex behavior, and as long as we require it to execute things online, then we will get this fundamental dissipation difference. So maybe by measuring heat dissipation or power outputs, we can benchmark future quantum devices to decide whether or not they're using quantum effects. More on the fundamental sides, one of the things I'm fascinated by is the potential for a dynamic second law, because it's possible to show that the memory cost for translating one sequence to another is different from the memory cost of doing the thing in reverse time. Now, if this also maps to thermodynamic dissipation, it will tell us that certain sequences are fundamentally harder to generate, or more natural ways. If we don't have a source of free energy, we can only go from one temporal sequence to another, and therefore we can get certain notions of dynamical free energy resources. And finally, as an outlook, there's always a connection, direct connection to machine learning, as people in the classical literature have been using these dimension-reduced models to demonstrate their ability to learn more quickly. So this was a paper done by Facebook where they showed that if we can build these more simpler models in there, then our agents get superior performance because they have a smaller optimization space of possible policies. And indeed, the objective functions can also be translated to energy harvesting functions. So there's certainly a lot of interesting ideas to explore between these fields. So I will conclude there and mention that these are the people involved. Jane really did the majority of the work sitting in the back. She's currently at A-Star, so feel free to talk to her about the details, as well as several of my postdocs who are involved in this research, who are now all gone to some pretty cool positions. So, and these are some of the publications that are involved. Thank you very much, and I will leave this with a job advertisement.
Thank you very much for this nice talk. So the floor is open for questions. Anyone? Okay, I see no immediate questions. I can ask one. So, there is a lot to unpack here. So there are a few things I think I did not completely understand. So as far as I see, the real thing that is quantum in what you're describing seems to be the quantum memory that you use, right? And so my question is, because you want to address this memory regularly without disturbing it, or disturbing it as weakly as possible, is there a connection to things like weak measurements and so on? Can you optimize the way that you address the memory?
That's a very good question. So actually in this case, the disturbance, we need it to be strong. So the weak disturbance, because we need the agents to be adaptive. So the part of the thing is that through the disturbance, we can engineer the disturbance so that the memory is updated exactly as it needs to be able to respond correctly to the subsequent time step. So actually, we're leveraging this feature of quantum mechanics. So this is one of the nice things. So if we try to correct for it, it would incur a lot of energetic costs. But because we're leveraging this behavior, it doesn't cost anything extra at all. Of course, we do need it to do it exactly the way we want. So if there is extra stuff leaking into the environment, then we need to correct for that. But the agents themselves operate on strong coupling.
Okay, that's interesting.
Yeah, so I have, maybe it's even a silly question.
Sure.
One of your initial assumptions was that you were not going to use the input as a work source. Or as a free energy source, let's say, because it could also turn it into heat. Is that always the right thing? Can you imagine situations where you could still do something useful, but just somehow using the energy that's in the thing that you're taking in because you don't need it for something else?
That's a really good question. In fact, there's a lot of situations where that's likely to be true. I mean, even if we're just thinking about machine learning, in many scenarios, the environment itself may have certain properties. That means that it precludes certain input questions depending on what previous input was asked. For example, if we take a look at a game of blackjack, a card game, drawing certain cards will obviate their probability of appearing again. And indeed, in the area of adaptive energy harvesting, the whole goal isn't to execute a strategy at all. It's that we have some correlations in the environment. We want to extract the most energy from it. So you can think about us as doing the reverse of that. In adaptive energy harvesting, we have a pattern, and we need an agent to extract the free energy from that pattern. Here, we start with no pattern and no structure, and we want the agent to generate the structure. And when we combine these things, we end up with pattern engines that can go back and forth. And we can also look at sort of cases where we might start up with some resources, and what can we do with them. I didn't cover that, to be honest, because the formalism gets very complex. We have mathematical equations so far, but we can't say anything about precisely when quantum is advantageous. But it's definitely an area that we should explore. Thank you.
There is a question there in the back. So I'm not going to be too strict on time, I guess, given that we have nothing after the session, we can be...
Yeah, so my question is, if you restrict the set of operations on your target to free energy, non-increasing operations, so would that also restrict the kind of policies that you have to kind of thermal operations or likewise?
That's a good question. So in terms of the policies that we look at, so let me go to a general picture of our quantum agents. Over here. So in terms of the way that these thermal agents operate, is that actually we don't have any constraints on what sort of process that we do here. So this process here can be, So this process here can be absolutely anything. But the key thing with the information battery framework is that we need to take account of all the free energy that's required to generate this process. So this is why we go to the unitary dilation. But from the perspective of if you are simply engineering this physical process, the relevant part is just this P here that's acting on our actual agent system. The rest of this is kind of a theoretical construct, so we can analyze the minimum amount of free energy we need to be able to execute this particular process. This is why we say we find the optimal Stein spring dilation, and we find kind of like the minimal free energy change that we must induce in the battery. So you can think about this as all a theoretical construct. If we were to engineer this in the lab, we'd probably find the most experimentally accessible way to execute this quantum process. But the theory tells us a fundamental bound on how much energy is absolutely required, and also a way of achieving that fundamental limit using the framework of information batteries. There are probably other ways of achieving the reversible limit as well. Thank you.
Okay, so I think now we have to gradually move on. So let's first of all thank Ville again for this talk. And so the next speaker can come up.